Welcome to the webinar, vegetable grafting webinar. I see right now about 30 people connecting. So if you have a microphone, unmute it. Please mute that so that we don't have to hear your surrounding sound. Thank you very much. So I'm Cherry Kubota. I'm sitting in my office at Ohio State. I'm the host of the monthly vegetable grafting webinar. So today's speaker is Dr. Ricardo Hernández from North Carolina State University. Before introducing him, I just wanted to go over a couple of information. So this is the monthly webinar series we started last month, and then October webinar and November webinar, we decided to focus on grafting technologies. And then last month, as some of you may remember, we had a grafting machine introduction from a company in Osaka, Japan. And then today, Ricardo is going to share his research outcome and applications in producing high quality vegetable, grafted vegetable seedlings under electric lighting. So that's a quite unique application. And then January, February webinar is going to be more efficacy of grafted plants, some of the disease resistance and vigor enhancement and yield enhancement and all that. And March and April, how to use grafted plants, how to manage, how to change the practice. So those are the contents we are thinking. This webinar series is organized by USDA SCRI grant project grafting team. This is over 40 members across the states participating to do research and extension and then education all together. So one more quick information. The grafting webinar is designed to share the science-based technology and science-based information to our stakeholders. I like to introduce more scientific opportunity or scientific communication opportunity coming up in July. This team is organizing international symposium, second International Vegetable Grafting Symposium in North Carolina. So this is another great opportunities to meet scientists and then also exchange information. So more information is coming up in our website and then also the symposium website. So with that quick background introduction, I'd like to switch over to Dr. Ricardo Hernández. And then while he is setting up the screen share, I'd like to quickly introduce him, what is his background and things like that. So Ricardo, you can take over screen share. So Ricardo Hernández was born in Chihuahua, Mexico, and then his bachelor degree from New Mexico State University in agronomy, and then master degree in entomology from Texas A&M. And his PhD is from University of Arizona Plant Science Controlled Environment Agriculture Program, and he has also doctoral minor degree in entrepreneurship in the McGuire Center for entrepreneurship at University of Arizona. So, and then he's currently assistant professor at North Carolina State University, and he's going to talk about indoor production of high quality grafted plants, benefits and energy opportunities. So, Ricardo, you can take over.
Absolutely. So, a couple of things first. I see Giovanni join the chat. Can you please mute yourself, Giovanni? We're getting some background noise over here.
Yeah.
And yes. And thank you very much. Great. Let me get this ready. Okay. Okay, so before I start the presentation, I would like to acknowledge my graduate student, PhD student, Brandon Huber. He actually created most of this presentation because a lot of what we're going to present today is based on his efforts and the research here at NC State that is related to this SCRI CAP grant. So, so he does the work, I take the credit. That's how it goes. And then, so I just have a couple of introductory slides. And for this group, I'm going to go through those very quick because most of you are familiar with grafting, right? So we're trying to get the best of two different worlds, right? We're trying to get the best out of roots from the rootstock and trying to get the best out of our science. So that's why we do grafting, right? The history, slightly history, grafting is not a new thing. You know, it was recorded to be commercially available in the 1930s in Japan. And however, the more widespread adoption of this technology was in the 1960s, right? And however, in the US and Europe is more recent, within the last 10 to 12 years or so. So some of the benefits, like all of you know, here you have some references in case you want to dive deep into the research. But we know that I have soil-borne pathogen resistance. There is some studies actually doing salinity tolerance. Also, they can reduce temperature stress, reduce drought stress. There is a study working on heavy metal tolerance, and then increase of water and nutrient use efficiency. And the main one that we care the most is typically increase of fruit yield and quality of the yield. So even though the adoption in the US and Europe is within recent years, their adoption is rising. And here you have a tomato example, especially in the US. So here, the usage of tomato graft in the US, this is just an example. You can see around 10 million plants are used, and they're coming from either Canada, Mexico, or in the US. And then there is around 1 million plant used in high tunnels. We don't have exact numbers for that. And then open fields is the one that is increasing, and is around 6 million. And the retail market uses, you know, more or less, probably less than 1 million. So the demand for greenhouses is tightly correlated to the land, greenhouse land that it's built, so it's relatively stable in the US. However, the open field adoption for the fresh market is increasing. Right, so this is just an informatics, you know. If you can, this is again for tomato market in the US. It's segmented mainly in two big segments. You have your processing tomatoes, right? And we did a back of the envelope calculation to estimate the number of plants per acre, right? So it's around 314,000 plants. I'm sorry, 314,000 acres planted at a density between 7,000 to 9,000 plants per acre. And these are the processing tomato, right? So typically used for your sauces and everything that goes in the can. And then you have the fresh market tomato, right? So the fresh market tomato, it's around 95,200 acres planted in the US. And to calculate this number, we use the density of, you know, close to 6,000 plants per acre. And within the fresh market tomato, segmented within that market, you have the greenhouse, hothouse tomatoes, right, which is also part of the fresh market, and is relatively small, right, compared to, you know, 314,000 acres versus 977 acres that are coming from the greenhouse. And of course, the densities are higher. You know, they can be seen reports up to 15,000 plants per acre. You know, but you know, typically, you know, if you don't have high technology, you're ranging in around 10,000 plants per acre. The reason I show this slide is because the fresh market tomato in the outside the greenhouse is increasing their adoption for grafted plants, which is great, right? Now, let me give you an example here. You know, the field fresh tomato, this is just a fresh market. For now, I'm not talking about the processing market tomato. I'm just focusing on the fresh market tomato. For the fresh market tomato, we see that around 1% are grafted plants, you know, versus 99% non-grafted, right? And the greenhouse fresh tomatoes, where we have close to 75% of those plants being grafted, because the benefits for some of the cultivars are already well documented. So this demand, the demand is expected to increase in the field fresh market tomato. Now let me give you an example. These are pie graphs of the adoption of grafted plants in different countries based on these same references that Brandon extracted. And you can see here that our adoption right now is around 3%. Now, this is entire fresh market, okay? This includes greenhouses and open field, anything that is going for the fresh market tomato. Now, Italy is close to us, you know. France has adopted that. Now it's have around 50% of the tomato market is grafted. Spain is 26%, Japan 40%, the Netherlands 75%, you know, Korea 25%, and Vietnam is around 33%. And the demand for these plants is increasing. And we're gonna expect that increase in the recent years. There's a few factors driving this increase of grafted plants. You know, among them is the ban of metal bromide. You know, also just the reduce the increased regulation of pesticides in general, especially fumigants, and then also some issues with some of the alternative fumigants that are out there. And then we have less arable land, right? So you're trying to increase the yields also. And there is an increased demand for organic production. And typically, once you go organic and you want to combat a specific pathogens or diseases, and without fumigants, grafted plants are an option. So the problem that I'm trying to convey here is that there is not enough availability of high quality grafted plants to meet the current and future demand. Right? So the pie, if those fresh market field growers start converting more into grafted plants, the size of the pie is going to be huge, right? And then that's a good problem to have, right? And then, however, grafted plants have high production costs compared to non-grafted seedlings and require a specific expertise, right? And here I just have some a picture of fumigation of metal bromide, and also some examples of the main grafted plant nurseries in the U.S. That we get to hear more about. So one solution that our research program proposes, and this is part of the grant, is can we increase that availability of those grafted plants by using precision indoor propagation, right? Which is defined as precisely controlling the environment to precisely control transplant growth, right? So PIP is not specific just for grafted plants, but it can be for any propagative material. But since the grafted plant value is considerably high, it can be adopted for that. So the idea is to increase production, quality, and affordability of these grafted plants. So again, what is precision indoor propagation is growing transplants indoor away from environmental variability. And then this allows for complete control of the environment while maximizing the resources. Mostly is used with electrical lighting, which is LEDs, and the current efficiencies of LEDs are allowing for more crops to be propagated indoors in an economical, feasible manner. You know, and you know, there is several names to that, right? You can call it vertical farms for transplant production. You can use shipping containers for transplant productions, or you can even use large warehouses where you can control the environment. The benefits for this kind of technology is that if you have your recipes right, then you can have uniform plant growth. You also can have very high density because you're eliminating environmental cues that tell the plant they're under a high density conditions. You can sometimes manipulate the flowering of the plant. You can have consistent year-round production, you know, and then you can minimize pest diseases. You can maximize your resources, and then and it's also used sometimes to improve work environment. This is a picture of Brandon's setup for his research here in Wicked Crevets. So the overreaching objective of our contribution to this grant is to develop a low-cost, highly controlled containerized nursery technology to enable propagators of grafted seedlings to produce plants year-round with higher quality, available for the diverse regions independent of environmental constraints. So so how can we achieve that? Okay, so there's several challenges, especially when you talk about highly controlled, and mainly when you talk about develop low cost, right? So nothing from these pictures gives the sense that this looks low cost, right? But that's the main challenge, right? And amongst those challenges, you know, it includes high capital costs, high energy usage compared to either greenhouses or other low technology, high tunnel control environments. And a lot of the cost is driven by the electrical light used to drive photosynthesis, right? So that's a cost that does not exist in the greenhouse because typically we have the sun and the sun is free. But and the variability of the quantity and quality of sun is high even in the greenhouse, right? So we decided in order to make this overreaching objective, we needed to divide this objective and try to reach segments of research to achieve that. So we decided to focus on the main problem, which is right now high capital cost because you need to buy lots of lights and other things, and high energy usage. So this is advanced plant physiology. That was a joke, by the way. So you have here the plant. You have your basic photosynthesis. You need light energy and carbon dioxide. You also need a lot other components to make this to have the plants optimized for photosynthesis. But let's focus right now on light energy and carbon dioxide, right? So we know that just like in Vegas, cash is king. For plant production, light is king, right? So the total amount of light that you can receive in an area for an entire day, that's called the photosynthetic daily light integral, right? So it's a good analogy of this daily light integral is like a rain gauge that you put outside, right? So after a rainy day, you go out and check your rain gauge, and you're going to know how many millimeters or how many of inches of water you're getting per acre, right? That's a measurement. So we measure photons of light the same way, right? But this instead is the amount of photons of light that fall in a 1 meter by 1 meter area in an entire day. So we call it daily light integral. And the units are moles, which are photons of light per area meter square per 1 day, right? And this measurement is very important because there is high correlation between this number and the increase in growth. How correlated it is? Well, it's linear. 1% increase of this number of light equals 1% increase in yield, right? So that's the rule of thumb. So light is king. It's very important. However, another very important component is CO2, and we often tend to underestimate the importance of CO2 because is not easy to see. You need special sensors to measure, and also typically the ambient provides adequate level for plant growth, right? But but CO2 actually, plant physiologists define photosynthesis has the movement of CO2 gas from outside the plant into the chloroplast, and then eventually photosynthesis gets carried out. Of course, you need the light energy to carry this out, but this is a limiting factor, CO2 diffusion from outside the plant into inside the plant in order to increase plant growth and photosynthesis, right? Now, there's several aspects that influence that movement of outside CO2 to inside the chloroplast or plant. This is just imagine this is a leaf, and this is inside the leaf. This is the chloroplast. This is outside the leaf. Can you guys see my cursor? Yes? Okay, and then CO2 gas is moving inside the plant. Okay?
Yes.
So, great, thank you. So one of the main factors that affects this is the concentration of CO2 in the air, right? And the concentration of CO2 inside the chloroplast. So if the concentration in CO2 of the air is higher than the one in chloroplast, CO2 will diffuse to the chloroplast, right? So adjusting this concentration to a higher level will increase that diffusion, assuming that we take care of all the resistances, right? So the idea here is that there is some research done that, for tomato growth can be increased up to 34%, by increasing CO2 levels to 700 parts per million. Just to give you an idea, the ambient CO2 level is 400 parts per million, right? So by increasing to 700, there are studies showing that tomato can increase dry mass by 34%. Other similar studies also have a yield increase of many crops ranging between 20 to 30% when you grow plants under elevated CO2. And then, and like I said, elevated CO2 stimulates higher photosynthesis. So the objective for this experiment is, can we reduce the amount of light needed, since it's a huge factor on the cost, not only capital cost by buying lamps, but also the production cost by paying for the electricity of the lamps, and at the same time increase the CO2 and have same and maintain the plant quality, right? So, and you may think, well, yeah, I'm paying less on lights, but I'm gonna have to pay more on CO2. Well, there's some studies showing that if you apply CO2 under contained environments, which is what we're talking about right here in this precision indoor propagation system, is typically inexpensive. And we'll talk more about that in a second. So here, there is, for the research I'm going to show you next is mainly related to tomatoes, right? So Brandon tested two scions, Belsky, which is an indeterminate greenhouse tomato, very expensive seed. I find out while we were planning this research. And then Florida 47, which is a determinate field standard tomato. And then he used two rootstocks, Maxi4, which is widely known by all of you in the grafting world. And then another Xinjiang that is typically important in a part of North Carolina because of the bacterial wilt resistance. So the point is, he was growing different cultivars under the environmental conditions. Then we decided to test three different CO2 levels. The ambient CO2 level, which is around 400 micromoles per mole, which is the same than parts per million. An elevated CO2 of 1,000 parts per million, and the main reason we choose this number is because the literature says that most of the benefit for plants is between 400 and 700, and after 400 and 1,000, and after 1,000, the benefit diminished. However, no research has done on seedlings. And then we decided to really take it out of the park and have a four times increase of CO2 concentration. And then we decided to use three different light levels, right? So light intensity of 100 micromoles, like I said before, that would transfer for 18 hours, that would transfer to 6.5 moles of light per every meter square per day. That's for indoor production, that's considered low. That's a very low light level. And then we have 150, which is 9.7 moles per meter square per day. And the 200, which would lead us to 13 moles per meter square per day. Again, the day being 6 to 18 hours long. So we have, this is probably the considered low, medium, and normal, right? This is 13 moles a day, still a low amount of light. But to grow seedlings in general, it's a good number, right? So our control will be, this light level under ambient CO2 conditions, right? So we know that grafted plant, that seedlings grow well at those conditions. So in general, we just want to show you. So we try to hit the 400. The actual average CO2 concentration inside of that chamber was 440, so pretty close. Tried to hit 1,000. We were pretty close to 1,000. We had to hit the 1,600, and we were pretty close to the 1,600. Have here the night. The purpose of this slide is to show you that the experimental conditions between the chambers were very close, and other than the CO2 and the light. So here you have all the students and working on the harvesting, and you have here Brandon. And then we collected many different morphological and physiological and also growth rate measurements. But today we're just going to focus on three important ones that are more related towards grafting, which is the dry weight we would typically use to describe growth, plant height, which is important for grafting purposes, and stem diameter, which is also our trigger to decide when the plants are ready to be grafted. So overall hypothesis that we have before we started this experiment, was that with CO2 at a 4 times higher than ambient, and with the light half of the required light, we will produce equal seedlings than your control, which is 13 moles of light and ambient CO2 concentration. And of course, we developed this hypothesis based on existing literature for other crops. All right, so let's see if we can hit that. So let's move a little bit into the results. So here, just bear with me. Here you have the DLI. DLI is the amount of light, right? Is the amount of light for 1 day, the average amount of light for 1 day, right? So here, 13, like I said before, is our control, right? This is how much light we need to grow decent seedlings, right? So, and then, you know, this is our ambient CO2. So every line represents one of the CO2 concentrations. And then here you have your other light intensity, which was 150, which is close to 9.6 moles per meter squared per day. And then you have your lower light intensity, which is half of the control, with only 100 micromoles, which gives us around 6.5 moles per meter squared. And over here you have dry mass, and that's how we qualify the growth of the plant. Typically, a plant with a higher dry mass is a plant that is much better in terms of young plant on transplant. You want those plants to have high dry mass to be able to say that the growth was optimal. So if you see here, this is our control, like I said, ambient CO2 and 30 moles of light. So this plant right here will have around this much dry mass, right? So around 33 milligrams of dry mass, right? So that's our control. That's the quality we're looking for, right? So what happens when we increase the CO2 at a different components, right? So now here you have two lines. The orange line represents your treatment that has 1,000 parts per million of CO2, elevated CO2. And then you have your line that represents the 1,600 CO2. And again, you have those three dots of the different light intensities, right? So we follow this line right here. Like I said, this is the dry mass that we're trying to achieve to have the same quality than our control. We can see we drive it all the way to here, right here in this intersection. And in this intersection, it means that at this light level in this CO2, and that at this light level in this CO2, we have the same dry mass of the growth of this plant. So we compute that, is saying that at 1,000 parts per million, with 9.3 moles of light, 1.2 moles of light, we have a 29% reduction in the amount of light needed compared to our control. Right? So that's huge. It was 30% of the light that we originally needed. Now we can save if we elevate the CO2 by 1,000 parts per million and have the same plant growth. Now what happens when we actually elevate it at 16 parts per million? My hypothesis, which was different than Brandon, was that after 1,000, we wouldn't see anything. But you can see here that seedlings, especially tomato seedlings, which like a lot of light and apparently a lot of CO2, you know, 7.1 moles of light at 1,600 parts per million gave me the same growth than my control, which means a 45% reduction in the amount of light needed to get that plant to be of the same growth parameter, right? And then now this is the output for all 4 cultivars, because they pretty much behave the same. And then we repeated this experiment 3 times. So we're very confident on these results. I don't know if you can tell, but I'm very excited. So let me show you some pictures now that Brandon prepared here. So this is now specifically for Rebelsky, and this is at 14 days after zone. So, right? So here you have your ambient CO2 and your 13 moles of light. This is our control. You have a stem diameter of 1.6 millimeters, and you have a dry mass of around 28.5. Now this is 14 days after seeding. So now here you have your elevated CO2 4 times and half the light, right? So you can see how like the dry mass is exactly the same, right? And you can see that the stem diameter is also the same, right? So the plants, they look different, right? So you can tell these plants are a little more stretched, and this is probably mainly related to signals that they can detect that is a lower amount of light. But overall, they're not, I wouldn't consider those as stretched plants compared to other ones grown, you know, in high tunnels or greenhouses. Now these plants here, they have, you know, twice as much light. You can see they stay a little more compact, and also you start developing some anthocyanin in the leaves, right? Which is, but overall, in terms of growth, is the same plant. They have the same dry mass. So now let's talk about stem diameter. All right, so here on your y-axis, you have stem diameter. We typically graph when tomato reaches stem diameter of 1.8 millimeters. And then here now, it's not light anymore on your x-axis. What we have here now is the days from zone, right? How many days until you can get that grafted plant ready, right? So grafting threshold, right? So here, we have a combination of treatments of light and CO2. Don't worry about too much about this light. It's very busy. We'll make it more specific. But just to give you an idea, this red line, is 200 micromoles of light and 4 times the CO2. So this is like the luxury conditions, right? So you can see here in this point, they will reach the grafting time much sooner than the one, for example, here, which is 100 and 400 CO2. So let's tease that out a little bit, okay? So the first thing I want to show you is that these two lines, 100 and 200, 100 are 1600 parts per million of CO2, and 200 of light at ambient CO2, right here, are exactly the same. So they both will reach the grafting time in 16.6 days, right? So basically what I'm saying here, you can cut the light in half if you increase the CO2 by 4 times, right? Now let's look at the best of everything, right? More light, more CO2, right? So you have a line like that. So it means if you are saying, well, I really want to speed the growth of my grafting cycle, and so I don't have issues spending more money in the light. If I can get more cycles, then you can, reduce that by almost 2 days, so you can have the plants ready to graft in 15 days, right? So let me show you some pictures here. So this is again, this is Rebelsky, and in each treatment, the pictures right here means all these plants in this slide have reached the stem diameter of grafting, which is 1.8 millimeters, right? So this is the control, ambient CO2 and 13 moles of light, right? So we hit the grafting stage at 15.4 days, and the dry mass was 45.2 milligrams. Now we half of the light, 4 times the CO2. We also reached it up at 15.4 days. Specifically for Rebelsky, the dry mass was the slightly less, right? And then we have the best of both CO2 and light. And then we reach the grafting stage in 13.6 days. And we have a dry mass higher than your half light, right? But typically the same than control. But we speed up the growth. And like I said, the plants do look different, morphologically speaking. However, all those plants have reached the grafting stage of 1.8 millimeters, and they're ready to go grafting. So now we have Rebelsky, but instead of matching the grafting day, the stem diameter, which is 1.8 millimeters, these are pictures shown when you harvest in the same day, right? So in this slide, I show you that these plants will reach grafting stage 2 days earlier, and this one will reach at the same time, and those are the characteristics of the plants. In here, I want to compare the plant growth when they're harvested at the same day, so they were under their conditions for the same number of days. So again, you have your control. You have a 1.87 millimeters stem diameter at day 16, and this is the dry mass. Then you have half light, at day 16, you have less dry mass, same stem diameter. And then at the end, you have your 16 micromole, which you have way more higher stem diameter and more dry mass, right? So you can see that, this is really pushing the growth of the plants. This is another picture, and you can see the treatments here. This is the height of the plant. And then this is your light levels on red, and this is your CO2 levels on black, okay? So let's go back to that hypothesis then. Well, initially I said that, or Brandon said that CO2 levels are 1600, which is 4 times greater than ambient, will allow us to reduce the light by half, so to produce equal seedlings. So what happened is it was not quite 6.5, right? So, but we could reduce the light to 6.8 or 9.2 and still have the same quality seedlings. So we were very ambitious with the hypothesis, but I think the result overall, if you're using dry mass as a comparison, is very well. Now, if you only compare and your only threshold is 10 diameter, then you can really lower the light to half, because you reach to that grafting stage at one point at the same number of days, but the plants in general will have a smaller growth rate or less dry mass. So to summarize, the DLI, which is a light, can be reduced 44% while still producing the similar dry mass when CO2 is elevated 4 times when compared to the control. And the production time can be reduced as much as 12% to days while still obtaining the same stem diameter if you're adding more CO2 and more light. So let's discuss a little bit, right? So I just mentioned that you reduce the light cost by 44%. Or we can reduce the production time. But we adding costs. We adding more CO2 into the chamber, right? So how do we level this off? Is this more expensive than the light, or are we gonna just end up with the same, right? So to determine this, we need to do a few calculations, and I will not go through any of those details, but we need information such as the total lamp number, the total electricity of the lamps that are using, the wattage of each lamp and how many lamps of those we use in the system, the CO2 cost in the CO2 use, right? So, first we calculate the lamp number, right? And this is actually based on several things. It's based on the intensity that you want to give the plants, either 100 or 150 or 200. It's based on the height of your system, on how high the lamps are from the plant. It's also based on the reflectivity of the system and the overall geometry of your system, right? So after we know the number of plants, then we can calculate the electricity used by those plants to grow, right? Now, to calculate the CO2 use, it's slightly more complicated, but it can be done. So basically, here you need to forget about this formula. In general, if you focus on the picture here, we need to know the CO2 concentration inside your chamber, right? So in this case, for example, it can be 4 times ambient, or it can be ambient. Doesn't, whatever, you need to know that number. Now you need to know the concentration outside your chamber, which we can assume is ambient, which is 400 parts per million. Then a number that is very important is how leaky is your chamber. Is it very sealed or is it very leaky? If it's very sealed, it's going to be more economical to add CO2. If it's very leaky, it's going to be less economical to add CO2. And the third component, that very important component that we need to know is how much how much CO2 the plants are taking, right? And that depends on the photosynthetic rate of the plant, and that depends on how many plants you have in that system. Okay, so those are the main things that you need to know. So let's go to the calculations here. So number one, here you have in this graph, you have your light in CO2. So your control again is 200 micromoles and 400 parts per million of CO2. It took us 16.6 days to graft on average, right? You have your nest treatment, which is half the light, 4 times the CO2. It took us around the same time to graft, right? And then you have your nest treatment, which is the standard light, but 4 times CO2, and it took us around 1.5 to 2 days to graft. Sooner to graft, right? So there is some advantage this. Light cost, right? It cost me 34 cents per tray in light cost for my control. It cost me half if I reduce the light in half. And it cost me 9% less than my control if I increase the CO2. Why? Because we have the plants in the system less time, 15 days instead of the 17, 16 and a half days. So that's the light cost. So even by increasing the CO2 4 times, I still decrease my light cost. Now let's look at my CO2 cost. My ambient CO2 is around 1 cent, per tray. Now, if I'm increasing by 4 times, so 4x increase, it means a 300% increase on that, right? Same here, we're increasing the by 300%. And here we might think, well, that's a huge increase percentage watch. Yeah, but this is only 1 cent. So the overall total cost of the plan, our standard control, is at 35 cents per tray. And our half light, we have reduced that by 43%, by adding the CO2 cost and reducing the light cost. And if we just want to speed the plan and finish faster, we still have a reduction in electricity. So by adding that extra CO2 and keeping the standard light intensity, you still save in the total cost because you're finishing those plants sooner. Now, I want to point over here that these calculations were made with a area exchange of 0.5. So that's not a very sealed chamber, it's considered, leaky, but if that number is smaller, like 0.01, then with a very tight chamber, sealed chamber, then those numbers are even better, especially for the ones over here. And now let's compare the dry mass, which is actually a growth. Well, even though you can graft in 16.7 days, same than your control, you still, the dry mass is 6% less, right? So the plant did not grow the same than your control, 6% smaller. But here, your dry mass is 30% bigger. So not only you get to that grafting point faster, those plants have 30% more dry weight, so they're bigger. Right, so in conclusion, 13 moles and 1600, right, the best of both worlds, light and CO2, produces the fastest transplants in the most dry way. However, the most cost effective would be half the light and 4 times the CO2. CO2 supplementation costs only 10% of electrical utility cost, and we can get savings up to 43% on production costs by adding CO2. And then with this data, growers can decide if they either want to speed up the growth or if they want to reduce the operational cost by their light CO2 combinations in their facility. So now so that was the work in tomato. There's also work being done in cucurbits here by Brandon. He actually in the middle of this experiment, and he's testing watermelon and the same reasons. After he's done with the cucurbits, he's gonna work on compare the output to a greenhouse production output, including a greenhouse with and without supplemental lighting, and doing it through an entire year to find those months where the greenhouse produces the same quality grafted plants and those months where the indoor chamber produces better plants. And then the economics are going to be worked out into these research to compare the production cost. And then another thing, he's going to design experiments that can test the transplant shock, right? So we're growing these plants in a complete indoor environment where they're not looking at, especially UV light, and also when the plants are not seeing, high amounts or heat or infrared radiation. We want to test those conditions and see how they react under different pressures of light and temperature. So, the work that he's currently working on, he's working on joyride and fascination. And also he included a Katrina cucumber just for references. And Rostock is working on carnivore, which is an interspecific squash. This is just a photo that he took very recent. With the cucurbits, we may have a slightly different story because the amount of time we keep it in these chambers is very, very short. So I'm looking forward to analyze this data and share with you in the near future. So Cherry also asked me to give an example of some of the, share with you the efforts to bring in some of indoor production technology and knowledge to a commercial sector. So there is a company here, and I just want to disclose that I have a stake in this company. It's called Grafted Growers, and they actually this is the only company using in the in the Americas using indoor production of grafted seedlings. And the company was actually the main source for the initial funding for the company came from 2 USDA grants for small business research innovation grants. And the second grant, which was recently awarded, allowed the company to create a small-scale commercial prototype. And that small-scale commercial prototype is now being opened here in North Carolina. And so hopefully the doors will be open here soon. And so the value that the company expresses is that using optimized environment. Of course, this company has its own internal research on how to optimize growth of transplants, and that was done through the SCRI grants. And then, so that's one of the value propositions of the company. Of course, uniform growth year round. This is in general for anything grown indoors. Smaller disease and pest free. It's less incidences of this pressure, faster growth, and etc. Right. So the company is working a lot on the technology that allows for this faster growth, right? So the idea is to get to that grafting point faster, right? To get to that 1.8 millimeter faster, so you can have a shorter cycles for grafting and accommodate more plants. And then also one value added for this is that the overseeding percentage is very low compared to what we are used to in when we're trying to produce grafted plants. So we seen overseeding percentages, of around 40%, or in this case 25%, to compensate for those losses, that you get during germination and when the plants don't really match their size to be grafted and after healing. So it's actually a sound practice to have overseeding. However, that creates a pressure for the grower because they provide the seed, and like I said, some of those seeds may be pretty expensive, especially the rootstock and some of those greenhouse scions. So the company is able to do, 97 to 90, 92 to 97% conversion rate. So the overseeding rates, are close to 10% compared to other greater overseeding rates that we're used to in the grafting world. So I want to give credit to Brandon. So Brandon is my PhD student. He's also an avid gardener. He has raised this plant for the past maybe, I don't know, 10 years. This is a titanium arum. It's a corpse flower. It's the largest flower in the world. And he has one here at the greenhouse, and it flowers every, I don't know, every 5 or 10 years. And he recently flowered here. So that's Brandon. And he also, grafted a tomato, a watermelon, and won 9th place in the watermelon competition, the largest watermelon competition. And then he actually could have won maybe 6th place, but 2 of his watermelons were disqualified because they had a small crack or something like that. But so we're very happy to have Brandon with us. And acknowledgement to the team. We have Cherry Kubota is a good collaborator, very good collaborator, instrumental for our work. Christian does a lot of the technical support and system design. We have the Phytotron, which is a building where we can host a lot of plant production chambers. My grad students and technicians, and John Jackson, who is the president of Grafted Growers. And I'm open the floor for questions now. Thank you, Cherry.
Well, thank you so much, Ricardo. Wonderful information from science and application. So I like to take, we have still, a little bit more than 10 minutes. So right now we have 40 people in the webinar. And if you are comfortable, use your microphone, turn on the microphone, unmute, lower left corner. You should be able to find the icon and unmute it and then speak up, or you can type up in the chat area. So the first question I see in the chat area is, what is the impact of grafted vegetable for organic production? That's more general question, Ricardo.
Okay, so basically, if you're able to certify your plants to be grown in the grafted plants to be organic, then you give that resistance, and it comes very specifically to the issues that you may have in your particular fields. But if you have a specific pressure of, for example, bacterial wilt, you can find the rootstock that can combat that or tolerate some of that disease pressure and be able to grow in that field without having to fumigate. And so that's very field specific, and it's typically better to give those recommendations based on the specific diseases that you have in your fields.
Yeah, so I think it's a very good tool, right? Additional tool to manage disease and pest in organic production. Relate to that, Ricardo, can you grow organic seedlings in your indoor facility? Is it okay to do now, or is it not allowed to do?
Yes, the facility is organic certified, so yes.
So, but that's only for US and Mexico, maybe? You know that.
So it's certified by the California Organic Certification. So I'm not aware. I need to check if that applies for Europe, but they went through those recent changes, so I do not know the answer to that question, Sharon. Yes.
Okay. All right. So what about oxygen concentration while changing the CO2? Another question.
Oxygen concentration inside the chamber?
Yeah.
Very good question. So, you know, when you compare to what the air is composed of, even increasing the CO2 four times, is still in the parts per million. So, and in the overall sense, the amount of oxygen in the chambers is still abundant and plenty, even, you know, by increasing it 4 times. So no issues with that.
So if you have people in that chamber, you don't have to worry about
No,
oxygen, correct?
I think when you have to go to levels to 10,000 to start, so for our bodies to start noticing that high concentration
Of
and
CO2.
of CO2,
Yeah.
and over that is like think dizziness. But you know that's 10,000, and the most we raised it here is 1,600, 1,600. So yeah, we're still within the very below the safe levels. Yes.
Okay, another question. What is the startup cost to add CO2 enrichment system to the facility?
So that's a good question. So, and the main cost will come from the control system, which is the CO2 sensor and your solenoid, and then the indirect cost will come from the CO2 tank. In this presentation, I show you the cost of actually using the CO2, which is very minimum. Now, the cost of adding that technology compared to adding lights is very small. It's very small. To give you, let me try to do a quick math. But to have $1,200 of light for one level of growth, you only have to spend around $300 or less for the CO2 components. Now that depends on the size of the facility, and the CO2 components. Typically I can take care of large facilities.
Yeah. Okay. Great. So since we are talking about cost, I have a quick question, Ricardo.
Yes.
So you said 34 cents per tray of lighting cost, right?
Yes.
Electric cost.
Yes.
How many plants in a tray?
This is excellent. Actually, we have Brandon here. Brandon, can you please answer that question?
Brandon, you need to turn on the mic. Yeah.
Hey, hello everyone. So the trays we used were 144 cell.
144 cells. So if you translate that cost to per plant cost, that's basically less than 1 cent per plant.
Yes.
Yes, for electricity. Yes.
Yeah. So that's quite. I think it's very low. I mean, it's nice. Probably everyone might think that electric lighting is the super expensive thing to do, but this type of production, less than 1 cent per plant.
Yes, and
Good.
it goes back to the density. Yes.
Good. Thank you. All right. So anyone want to use microphone? Or I go down the list of questions. Any pest pressure difference with high and low CO2? Well, you don't have pest pressure, right?
Yeah.
If
So that's
yeah.
interesting question. We didn't have pest issues here, but that would be a good research study to see how these environments affect pest pressure, either pathogens or pests. We didn't get to that point. We didn't have any issues here, but of course we're very protected here under several layers of buildings. Yeah.
Yeah. Okay. So Ricardo, I have a very scientific question. So you had shown that CO2 enrichment is very effective, and then you can reduce the light intensity, right, by CO2 enrichment. But you had a little stretch because of the response to low light. Can you change the spectrum?
Yes.
So that
Absolutely.
it makes a more compact plants.
Yes. Yes.
And then, are you working on that, or you?
Yes. So we didn't focus too much on that stretch because something that I didn't put in the presentation is that we actually stretching the plants. We in this experiment we're stretching the plants to be able to have enough room for grafting. But if we give a light signal with infrared that actually makes the plants to stretch. If we take that light signal out, all the plants become very compact. So maybe under the high CO2 level of light will become actually, not that compact and be acceptable for production. So that's a good point. So in this experiment, we are actually stretching the plants.
Okay.
Thank you, Chair. Yeah, good point. Yes.
All right. Okay, so somebody is saying OSHA guidelines suggest that anything over 1,000 parts per million CO2 is considered inadequate ventilation, although it doesn't mention greenhouse environment. Oh, this is not greenhouse, by the way, gross chamber environment. What do you respond to that?
Well, I tell you what our experience here. Our university OSHA required to have a sensor in the window to make sure that those concentrations don't go higher than than what we expected in case you have a leak in the tank. But other than that, we didn't have any issues in the university, which the scrutiny is pretty high. Yes.
Yeah, but then I think the OSHA's guideline is based on CO2 because CO2 is easy to measure and the indication of the ventilation, right? Rather than CO2 itself is harmful at that level, 1,000 parts per million.
Yeah, I'm less familiar, but I think this is related to office space.
Right.
How you can ventilate office space when you have a lot of desks in one room. Yeah.
Yeah. So it's not for the CO2, but ventilation indication.
That's right. That's right. That's right. Yeah.
Okay. Anyone else? Anyone wants to jump in? We have a few more minutes.
Yes, I do have a question.
Go ahead.
We're planning our nursery greenhouse for this for tomato as well. But I'm wondering how hard would it be to keep the CO2 concentration in our greenhouse? We're planning to do the 5-meter high. And second one, we grow in Mexico in a very sunny place and in a very sunny season. But I'm wondering if it's still in this place and season, is it still affordable to use supplemental light?
So it depends on the levels of light that you have inside the greenhouse. And I think this specific objective is for grow chambers, right? So elevating the CO2 higher than ambient in a greenhouse that has a high ventilation rate or room air extension, it's probably not a good idea. However, there's other reasons to actually enhance the movement of CO2 from the air into the plants within your system, which is basically what we're trying to do, right? So one of those is move air around the plants. So if you're able, you can buy a sensor that the HVAC contractors use to measure air velocity in docks. And if you go and measure that air velocity to be close to 0.3 meters per second around the plant, then you're ensuring that the air is moving around the plants and the plants are taking CO2. Okay. Now, I don't know about the amount of plants in your density, but we also seen that CO2 around the canopy level of these plants is actually lower than the ambient, right? So you could supplement CO2, but the threshold should be ambient. And then you should measure the CO2 at the plant canopy, because then you're not wasting CO2 outside, because if your levels are ambient, your system doesn't turn on, right? So if you can put a sensor at the canopy level and you can deliver that CO2 to the plant, and you put the threshold to be 400, then you're not wasting the CO2. You're only adding the CO2 used by the plants.
Yes,
right?
only in the canopy, yeah.
Yes, and then, say that again, Giovanni, sorry?
Sorry, what?
Oh.
Maybe somebody's.
Yeah, and so regarding the light level, yeah, it depends on your area, right? It depends if you're having issues with the plants not growing uniformly or having issues. It really depends on the area. You also have to consider the light quality. If you're mainly having stretch issues, it might be related to the light quality, so that supplemental light can help with that. But yeah, it would depend on specifically on the structure and your glazing.
Okay, thank you.
All right. Anyone else want to use microphone and ask yes. Yes, go ahead.
Thank you. I'm from Cameroon, and I started vegetable grafting, especially tomatoes. My problem is, I wish to know if it is possible to grow the tomatoes with organic manure. That's, for example, like vegetable. The second question is to know if it is profitable to grow vegetables locally, because here in Cameroon we don't have, for example, those machines of calculating carbon or oxygen. So I wish to know if it's possible to grow the vegetables locally here in Cameroon. Thank you.
So Fabrice, let me try to rephrase your question and correct me if I'm wrong. Are you trying to get my opinion on if it's profitable and possible to grow vegetables, actually harvestable vegetables in this kind of technology in Cameroon?
Yeah.
Yeah, so there's a big movement on indoor crop production. It is a challenge, and I seen however I seen that a very positive aspect. So yes, technically you could. Now, can they be economically affordable or economically competitive to vegetables growing in the field? Maybe not, or maybe yes, right? So it really depends. But my suggestion would be to actually start with the transplant stage of those vegetables that will eventually go to the field, because now we know that it's economically feasible and that will help actually your field production. But if you didn't have but yes, you can grow vegetables inside these systems, not a problem.
Yeah, I think Ricardo's lighting data of 34 cents per tray probably help you to figure out how much cost would that be when you grow like 6 weeks of lettuce head or 4 weeks of lettuce head production, right? And how many lettuce head can fit in that one tray area. So I think that is a good starting point to find out the cost.
What
It's
about
gonna
the
be
organic?
organic.
Yeah, because I've started it, and the plants are already on field. So I wish you know, because I don't want to use chemical manure. I want to use organic manure. Is it profitable to use organic manure?
So yes, of course. You just need to make sure that the substrate, you're saying the substrate is organic based substrate, so it can be done. Yes, as long as your certified agency allows you to do electrical lighting and you have a substrate with enough nutrients to carry out the plant growth in the organic manner, and then you're just watering with regular water, then yeah, it's possible to certify that. I guess in my experience, yes.
Okay. Thank you, Ricardo. And thank you, everyone, for attending. Let's thank Ricardo one more time for a great presentation. And a little bit after noon right now, so thank you for attending. The next webinar is going to be January. And then the speaker is going to be Dr. Frank Rhodes from, again, North Carolina State University. So stay tuned, be in the listserv so that you get information. Thank you very much.
Thank you very much, everybody, for your time.